Um, each had a little bit different problem in the preview activity, but they were very similar in that we had some kind of density and we used that density to get a total number. So in the first one, we knew the density in cars per mile, and the integral gave us the total number of cars over a certain distance. In the second one, we had a density that gave pounds per inch, and we integrated over that density to get the total weight of a bookshelf from 0 to 72 inches. Same idea we're going to look at in a couple different contexts today is how do we take these continuously varying densities and use those to get a total. In our case, we're going to look at total mass and center of mass. Let's get into a couple examples, see how far we get. If we have some more time, we'll break back into groups and let you guys try a couple. Here's our first example. This one's going to seem very straightforward at first, and that is intentional. So first, let's talk about a rod with a cross-sectional area of 1 square centimeter and a length of 10 centimeters, okay? So here's our rod, and we've got a length of 10 centimeters. Cross-sectional area, so that would be the area of the circular end, is 1 square centimeter. All right. So the total volume of this cylinder is just 10 times 1, or 10 cubic centimeters. All right. Well, that's all well and good. Oh, guys, don't worry about that mic. Not a problem at all. All right, now let's talk about finding the total mass, and we're going to look at it in a couple different cases. Number one, let's just say the density is 2 grams per centimeter cubed. All we need to do to get this is the total mass here is multiply the volume times the density, and I'm going to use delta for density. Sometimes you'll see a delta, sometimes you'll see a rho. Sometimes you'll see that guy rho and for density. 2 reasons I'm doing this. Number one is because, well, this is a straightforward calculation because our densities, our volume is continuous and our constant, excuse me, and our density is constant. So all we have to do is take 10 times 2 and we get 20. Now, what would the units on this 20 be? Remember this first case, we're looking at delta as 2 grams per centimeter cubed. What would the units on the 20 be? This is similar to what you did in the preview activity. Think about the units on the 10 times the units on the delta. And remember that we want a mass when we come out of this thing. What are we thinking for units? And you guys crushed the preview activity. So I think I know you know what it is. I'm gonna wait. 20 what? 20 grams. All right, because this was in, if we think about multiplicative structure, this was in centimeters cubed times grams per centimeter cubed. Boom, boom. There's the grams. So, one of the things I will do a little bit in this section and also the next section is talk a little bit about units to make sure we're making sense of the problems and the structure. Now, this did not involve any calculus. This is a basic multiplication problem, okay? If the density is constant on these rods, because the volume is constant, wherever I take a slice, it's the same. It's just a multiplication problem. But the reason I had you warm up with those activities is I wanted you to see the multiplicative structure within the integrals. the volume times the density in this case, okay? So now let's start to talk about if the density is varying, okay? So now let's give the density a function. How about e to the 0.1 grams per centimeter cubed? All right. Same rod. It's still going to be 10 centimeters long, cross-sectional area of 1 centimeter. But here is what's interesting. We now have a varying density. Sorry, there should be an X on there. 0.1x. If it didn't have the X, it'd be constant. This varying density is what creates the need for the definite integral. And I'm going to kind of walk you through the steps in this one because I want you to see the slicing. Because again, we're going to do slicing again on Tuesday. Like I said, permeates everything we do this section. All right, so I pick a slice. So that's going to be our ith slice. All of this is going to sound familiar. I know it probably is starting to sound like a broken record. Now, here's why we do this. We pick the slice so small that we can assume the density is constant on this slice, meaning the density on there, maybe we call it delta sub I, the density of the ith slice is e to the 0.1 x sub I, okay? Now remember, when we do the slicing, we're assuming that we're going to slice this into a bunch of equally partitioned slices. So we want to give that slice a thickness, or that common thickness, right? So we can give that slice the thickness of, let's say, delta x. Okay, so let's walk through the slicing on this one the way we've done in previous sections. First off, we're going to talk about the volume of the ith slice. Well, the volume is the cross-sectional area, which is the 1 square centimeter, times the height, which is delta x. This is in square centimeters. This is in centimeters. That means multiplying them together gives us centimeters cubed, which is the right type of units for a volume. And that's why I put so much emphasis on the units. They can actually help us basically check our answers. Okay, now let's talk about the mass of the ith slice. These are going to be steps that we're going to be doing on Tuesday too. So 1 times delta x, probably we would just write that as delta x. Okay, so we'll simplify that. Now the mass of the ith slice is the density times the volume of the ith slice. All right. So all we have to do now is take the density, which is our E, and this is just on the ith slice. So I'm going to put the sub I there, delta x. All right. I added the delta, which is this guy here, onto what we already had for V sub I. So we're kind of building in steps. Now our goal is to get the total mass. Now remember, we've talked about this before. First, at this point, we want to check before we go from sub I to continuous. Make sure these variables match. They're both in terms of x. We're good to go. So the total mass, now we're into the continuous case, e to the 0.1 x dx. And then what do you think x is going to vary from and to on our definite integral? What do you think the limits of our definite integral will be? We want to get the mass of the whole round. 0 to 10. Now, it doesn't say in the problem, we're assuming that this density is measured from the left end of the rod. So this definite integral is going to give us our total mass. Calculating this, you get 10 times e minus 1. Like I said, we're not going to spend a lot of time solving definite integrals. We did that back in the first module. So we're focused more on what to do with how to set these up this module. 2, 8, 1. All right, I've got a couple numbers here. This 17.18281. What are the units on it? And remember, this is just like the preview activity you did. We look at the multiplicative structure, v times delta, v times delta. That was what made up our integrand. So what will be the units on this number we just calculated? Perfect. Once again, it's in grams. Again, and I'm not trying to make these trick questions because I know the answers keep coming out the same, kind of like in the preview activity. I really want you to understand what's going on here, that the multiplicative structure, when I say multiplicative structure, I'm talking about this, the delta times the volume, multiplicative structure. That's what gives us the units, grams. Well, all the integral is doing is summing up a bunch of values of grams, just doing it continuously. Okay, questions about this blue example with the varying density? And these rod problems are actually pretty common. You're going to see a couple in the homework, and depending on how much time we have after these examples, hopefully you'll have a chance to try one today too. Okay. Now that we've got total mass, we're gonna, so we can generalize this. Basically what's happening is, here I used rho, or this P of X. Basically we run an integral from A to B, P of X times the cross-sectional area. Remember, for ours, the cross-sectional area just happened to be 1. So let's put that there as a note. A of X was 1. That won't always be the case. We'll look at one where it's not the case here in a little bit. And rho of X is the density. So that's that multiplicative structure that I'm talking about. The density times cross-sectional area times one of the dimensions. So this is basically giving us a volume, A of X dx, and then we're multiplying it by density to get a mass. So this is how calculating a mass falls into what we're focusing on this module. We have a continuously varying density. If the density is not continuous, we don't need an integral. We would do it with just the sum. But when we have a continuously varying density, it lines up perfectly for an integral. Okay, now let's talk about center of mass. The derivation of the moment is in the online lesson, so I'm not going to go through that. I'm just going to point out some really important things. The first thing is, if we're looking for x bar, check out what the moment is, the integral of the moment versus the integral of the mass. They're almost identical, except there's just an extra x in there. All right. The x accounts for the distance from the center. So here's what's really cool about this. Because we've already set up the integral for mass, we already know the integral for the moment. So if I want to calculate x bar for a rod, we're going to do the one that's in blue. All we have to do is the moment, which is literally just this integral with another x in it. The limits are the same and everything. X e to the 0.1 x dx over our m. We can put it in either form. I'm just going to put it in as f. Now, before we calculate this, let's do a little thought experiment. Okay, let's figure out roughly where this center of mass should be. So we've got a density that is increasing. E to the 0.1x is an increasing function. So we have a rod here. Let's say, let's put in a center on this rod. That's 5. Over here is 10. Over here is 0. Okay. So here's the question I want you to think about. If our density is increasing, should the center of mass, the balancing point of balance on this rod, should it be less than 5, equal to 5, or greater than 5? What do you guys think? If you had to guess. This is just kind of using some intuition based off the fact that our density is an increasing function. So think about, well, geez, is the density going to be bigger to the left of 5 or to the right of 5? Or is it going to be the same? If the density is the same on both sides, the center is in the middle. Just like our first example, if the density is constant, the center of mass is right in the middle of the rod. Now we don't have a constant density. So I kind of gave away that it's not at 5. So the question is, should it be the center of mass be over here? Or should it be over here? What do you guys think? And think about what it means to have an increasing density. That means it's more dense over here on the right side of the rod than on the left side. So we would expect more, the rod to be more dense over here and over here. So in order to balance this thing, let's say you had to balance this rod on your finger. Would you want to put your finger between 5 and 10 somewhere, or between 0 and 5 somewhere? I know it's not a perfect rod, but kind of think of like a baseball bat, right? A baseball bat is less dense towards the bottom end and more dense towards the less dense on the end you hold, more dense on the far end. Somewhere on this side, right? We would expect it to be somewhere between 5 and 10. And that's because between 5 and 10, the rod is heavier than between 0 and 5. And, we didn't do anything crazy to figure that out. All we said is, hey, the density is increasing, so it's going to be more dense over here. So the center of mass is going to have to be more towards the more dense end. The reason we're doing that is we want to make sure our answer makes sense. If we don't get an answer between 5 and 10, we probably have an error somewhere. Okay, so it turns out this top integral actually just comes out to be 100. This one is 10 over e minus 1. And this is, let's do it as a decimal because it's got to be a little more meaningful. Comes out to be 5.819767. Makes sense because we do have an increasing density, but it's increasing very slowly. So having it be just to the right of 5 seems pretty reasonable. Now, here's a question for you guys. This 5.8178 it's right here, I'm messing up the numbers. 5.819767. What are the units on this number? And think about what it is. It's not a mass. It's a location. And also think about what we did. We took an integral that we know its units were in grams. We added an x to it. So basically, this integral on top is the same units as the mass times the unit of x, but we're going to have the units of mass down here. So basically, the units of mass cancel out, and we just get left with the units of x. And what was x measured in? What was the other unit of measurements in this problem? Because what's going to happen, this number 100 is actually going to come out in units centimeters times centimeters times grams. This bottom one's going to come out in grams. Those are going to cancel, and this is in centimeters. Now, in the context of the problem, that makes sense because the center of mass is 5.8197 centimeters from the left end. Okay, so we can make sense of it mathematically, and we can make sense of it intuitively. Okay, questions about this, about the center of mass? What I think is so cool about the center of mass is, again, if you can set up the integral for mass, you can set up the integral for moment, because it literally is just putting the x in there and then taking the 2 and dividing. All right. So that's why we're kind of building this way. We did mass, well, then we do center of mass. And so now what we're going to do is look at the center of mass in 2D. Basically, what we just did holds for a center of mass in 2D and 3D. All right. So, and I don't want you guys to worry about this. We're not going to do a whole bunch of this. You don't feel like you have to write this down. I did put the link to this PowerPoint in the invitation today, and it's also in the course content. So if you want any of these notes later, you can always write them down. But look at this. The moment is just adding an extra x. The moment is just adding an extra y times the area in terms of y, or times the density times the area in terms of y. Add an extra z times the density times the area in terms of z if you got a 3D. Okay. Now we're not going to do any 3D in here, so we don't need to worry about that. It's basically the same principle in all of them. Now here's the caveat. To be able to do this, we do need to assume that we can get the density and the area all in terms of the same variable. It's easy to get in terms of x or our input variables. Sometimes it can be hard to get in terms of y, and sometimes it can be hard to get in terms of z. So we're going to talk about how to get around that. We're going to focus on a 2D though, because like I said, we're not going to do any 3D in here. All right. So this is great as long as our density is in terms of the variable we're integrating with respect to, or is constant. If our density is constant, this works out great to have it in these forms. You know, we did area between curves in terms of x. We've done area between curves in terms of y. So that's basically all that this a sub y of y is meaning. We throw in an extra y, no problem. The only concern we might have is if delta isn't in terms of y. So here's where this could be an issue. Let's say we have a metal plate with a density of 2x grams per centimeter cubed, squared, excuse me. So a metal plate is going to be a 2D object. As it has a shape bound by the curve x cubed and the x-axis between 0 and 1, x and y in centimeters, and we're going to find x bar and y. So this would work out perfectly for this one because delta is already in terms of x. This one would become a problem, not that we couldn't do the area in terms of y, but because our delta, it's in terms of x. Now, the derivation of this is in the online lesson, so I'm not going to use class time for it. But if we think of, you know, x bar and y bar in terms of their moments, and just to make this clear, x bar, I know there's m sub y, you know, why are the variables different? What m sub y stands for is the moment, which is the tendency to rotate around the y-axis. And if you think in terms of x, rotating around the y-axis would be a horizontal rotation, hence the x bar. Same thing with the y bar. So this m sub y, which is for x bar, is exactly what we just talked about. The density times the cross-sectional area, which is just the f of x minus g of x. For the one we're about to do, f of x would be x cubed, g of x would be 0. So this is exactly what we just saw. This is the one that's derived in the online lesson if you want to check it out. But what it does is it allows us to get the m sub x, which is the moment for y bar, in terms of x. So we don't have to do any finagling. Oh, there's an, and I look, sorry guys, there's a typo in here. Let me fix it. There should be, like I said, there's an extra x in there. Sorry. Yeah. X times our density times the cross-sectional area. Whoa, this is the right spot. Sorry, I don't like that. I have a mistake there. I got to fix there. Okay. I'll make sure I fix it in the one that's online too. Okay. Sorry, density. There's that extra x. This is doing the cross-sectional area. All right. So putting this together, here's our y bar and our x bar. And now let's try this with this problem. All right. And I know these formulas are messy. Do not think you have to memorize them. I would give you these are formulas I'd give you on the exam. Okay, so first off, let's take a look at the graph to see, whether or not we can get an idea of where x bar and y bar should be. All right, so if we bring up our graph, so here's the graph of our situation from 0 to 1. So this figure here, this curved triangular figure, is our region. This is x cubed from 0 to 1. Okay. Now, if we had to try and figure out x bar, and notice what's happening with our densities. X gets larger, this thing gets more dense. So if we had to figure out x bar, would you expect x bar to be bigger or smaller than 1? Then let's say a half. Half's going to be about right here. So what do we think? Should x bar be less than a half or between a half and 1? And you can put it in chat or turn on your mic. Let's just kind of, like I said, we just want to have an idea because we want to try to say, okay, this is going to make sense. We want to make sense of our answer. We can see, 0.5 is going to be about right here. We have a lot more of the plate to the right than to the left. Plus, we have a density that's increasing as we go to the right. So we're going to expect that center of mass in x bar to be over here. In fact, let's put in, if we put in those lines, so there's 0.5 for y, and x equals 0.5. If we look at this and we're trying to balance, think of it, what we're trying to do, trying to balance this thing, we're going to expect x bar and y bar to be here because this is our thickest, densest part of the plate. So we would expect x bar to be bigger than a half and y bar to be less than a half. Again, we do this because we want to make sure our answers make sense. Questions about that idea? Zoom in a little. Is everybody seeing why our x bar and y bar should, be to the right of this green line and below this blue line, somewhere in here? We'll get them exactly with definite intervals. Okay, oops. Let's look at calculating this. All right, so we're going to use these formulas, and I'm going to start with x bar because, again, that's the more straightforward. And if you got any questions as I go through this, please feel free to ask. Okay, so first thing we need is the mass. Actually, let's do the mass first. So let's talk about the total mass of that plate. Well, what we need is basically the area times the density. So the mass is going to be, well, remember, the area between x cubed and the x-axis is just the definite integral of x cubed. That basically gives us the area. And if we give a little more space here, if all I did was calculate this definite integral, this would give us the area. We go from 0 to 1. That's Calc 1 knowledge right there, right? That gives us the area that we're looking for. So to turn it into a mass, all we have to do is multiply by the density, or the 2x. So we get the integral from 0 to 1 of 2x to the 4th dx, which is going to be 2/5 x to the 5th from 0 to 1. If we put 0 in, we're getting 0, so this just comes out to 2/5. And we know that this is a total mass. What we did is we multiplied something in centimeters squared, the area, times the density, which is in grams per centimeter squared. So 2/5 grams. All right. And like I said, guys, feel free to ask questions about this. Now let's talk about X bar. Remember what I said. If you can do the mass in terms of X, you can do X bar, because all you do is you take your integral for mass, which we already said was 0 to 1 of 2x to the 4th dx, and you multiply it by an extra x. X times 2x to the 4th dx. So we already know that the mass comes out to be 2/5. Up here, we got the integral from 0 to 1 of 2x to the 5th dx. And integrating here, we're going to get 2/6 x to the 6th from 0 to 1 over 2/5. We could reduce that 2/6 if you want, but 2/5. So basically, we flip and multiply, and we're going to get 5/6. And now we're talking about X bar. X bar is some distance from the origin. So 5/6 centimeters. Going back to our graph. Okay, so 5/6 is a little bit more than 0.8. That seems pretty reasonable for this center of mass. Okay, so somewhere along this vertical line here. Questions about X bar? Y bar. Now for Y bar, we'll go to the formula. Okay, like I said, you guys will have access to this. I want you to see how it's set up. So 1/2. The limits on this are still the same as the limits on the bottom. So whatever your limits were for the mass would be your limits for the top. And then we've got our density, so 2x. And then our function squared minus our bottom function squared. Remember, g of x is 0 in this case because y equals 0, or the x-axis is our lower function. 0 squared. dx, we already know the total mass is 2/5. And so, let's see, let's clean this up a little bit. Those will cancel. X cubed squared, that's x to the 6th. So we've got, and then times another x is x to the 7th. So we have the integral from 0 to 1 of x to the 7th dx over 2/5. Add 1, divide by the new exponent. We have what, 1/8 to the 8th from 0 to 1 over 2/5. So 1/8 over 2/5. Once again, we flip and multiply. And we get 5/16. And again, centimeters. So nothing, the units are pretty much given in the problem. When we're looking at the mass, it's going to be in whatever mass the density is measured in terms of. When we look at the X bar and Y bar, whatever distance measurement the density is measured in. All right, questions about X bar or Y? Let's plot it then. Let's put it on as a point. So let's just see what it looks like. And then 5/16. And so there is our center of mass. And again, if we think about why this makes sense, remember, not only do we have more area here, but this thing has a density that's increasing in terms of X. So the further we go to the right, the more dense it is. If we had had a continuous, a constant density, we would have seen something more symmetric, and our point probably would have been over in here somewhere. So it's that varying density that makes this point in a spot that may not seem intuitive, but that's because our plate weighs more on the right as we go to the right. So not only does it weigh more because it gets bigger, but it also weighs more because it's got an increasing density in terms of X. One thing we don't want to see is something really obviously wrong, like the point not being in our region, or if the point was over here, we know it wouldn't make sense. If the point was up here, we know it wouldn't make sense. So again, that's why we just kind of do that little mental exploration first, just to say, okay, my answer should end up in this region in order for it to make sense.